In this ML safety course, we're going to talk about making systems safer more broadly. To make machine learning systems safer, it's not clear whether it's like making a car safer, a rocket safer, or a software program safer. So we need some basic concepts in hazard analysis that gives us a general framework for thinking about safety and risk. And so that's what we'll try and do in these upcoming lectures. Talk about some basic vocabulary for understanding safety engineering and risk more generally, and then we'll apply that to talking about machine learning systems. Let's start with some definitions. So first, a failure mode is a possible way a system might fail. This could be, for instance, like a system crashing. A hazard is a source of danger with the potential to cause harm. For instance, if malicious actors are misusing AI, that could be quite a hazard. Or if AI has goals that are different from us, that would also be a hazard. Vulnerability is a factor or process that increases susceptibility to the damaging effects of hazards. For instance, if a system is more brittle, then it's more vulnerable, so hazards can more easily damage it. A threat is a hazard with the intent to exploit a vulnerability. So largely just think of a threat as a hazard with some malicious intent. Exposure is the extent to which elements, that is, people, property, or systems, are subjected to or exposed to hazards. And finally, the ability to cope is the ability to efficiently recover from the effects of hazards. I should note that these definitions vary depending on the industry or the national governmental agency, but this is how we'll be using them throughout the course. The concept of hazards can be used to define risk. Risk could be understood as the expected hazardousness of various events. So let's consider some hazardous events H. Then we can consider the probability of those different hazards, and we can also consider the impact of those different hazards. If we multiply the probability and the impact of the hazard together and add them all up, that constitutes a definition of risk. It's possible to have a more refined understanding of risk. We could decompose risk into 3 factors rather than 2 on the previous slide. So the risk from a hazard is approximately something like the vulnerability multiplied by the exposure to the hazard multiplied by the hazard itself. Here we're meaning just the risk from a hazard, not the total risk. And multiplication isn't meaning exact multiplication, but rather just a nonlinear interaction. This is a notional description of risk. And here, hazard is a shorthand for the hazard's probability and its severity. So rather than consider the probability of the hazard and just the impact of it, we can decompose it a bit further to have a more precise understanding of risk. On the previous slide, we introduced a notional decomposition of risk. If we wanted to make it very precise and more mathematized, one could potentially write in the following way. This is largely just for instructiveness. You won't necessarily do this in practice. So risk could be understood as the sum over many hazardous events H, and we would need to compute the probability of that hazard actually occurring. And then if that hazard actually does exist and has non-zero probability, then we need to consider the severity of that hazard. Is it a big deal or is it fairly unimportant? And then if the hazard is existent and somewhat severe, if we don't make contact with it, it won't matter. However, if we do have exposure to it, that probability of contact is non-zero, and then we're more concerned. But then it'd still be modulated by our vulnerability to that hazard. I should note that we can consider the probabilities as basically being something like the probability of the hazard actually impacting us, and then severity and vulnerability are essentially some notions that help us better understand the impact of a hazard. We'll try to internalize some of these notions of risk through internalizing some concrete examples. Let's start with the example of falling on a wet floor, which could really injure a person. The risk from this hazard would be affected by the floor slipperiness. And our exposure would be affected by how much one is using the floor. And the vulnerability to this hazard would be affected by a person's brittleness. What are some ways to reduce risk from this hazard? How could we potentially reduce the hazard or reduce exposure to this hazard? Or how could we reduce our vulnerability to this hazard? Well, we could potentially use a fan, which would make a lot of the water evaporate and make the floor ultimately less slippery. We could reduce our exposure to this hazard by putting up a sign. Then people are much less likely to slip. So this will reduce exposure. And one could do something like strength training to increase bone density and make one's body less brittle, so that if one does actually fall, it won't end up hurting as much or won't cause as much damage. Let's turn to another concrete example. We'll consider the hazard of flooding. What's the risk that flooding poses? Well, we could decompose it into these three factors from before. The hazardousness would depend on the total rainfall volume, and the exposure to the hazard would depend on whether there's anything relevant there or not, such as people or important assets. And the vulnerability to flooding and the risks associated with that would depend on how low the area is elevated or whether there are unsuspended bridges and so on. What are some potential ways to reduce the hazard, reduce exposure, and reduce vulnerability to the risks from flooding? Well, it's not terribly clear how to reduce the hazard itself. Maybe in the future somebody could do something like geoengineering. At least for reducing exposure, there's a clear thing, which would be warning people. That could move people out of the area, and then they won't potentially experience flooding themselves. So at least they won't be harmed. However, assets might stick around. That would still overall reduce exposure, though. Some other ways would be, say, a levee. If people built levees, that might just reduce the overall vulnerability by preventing it from getting into the city in the first place and block some places from being flooded. As a third example, let's consider flu-related health complications. With this risk, there are multiple factors. One would need to consider the flu prevalence and severity, which affects the overall hazardousness. One's exposure to the hazard can vary too. You could come in contact with flu carriers, which would definitely expose you to that hazard. And vulnerability could be affected by whether you are of old age or in poor health. What are some ways to reduce the risk from flu-related health complications? How could one reduce the hazard? How could one reduce exposure to the hazard? And how could one reduce vulnerability? Well, one could wipe out some of the hazards, literally, by reducing the prevalence or the existence of the virus on surfaces. Another way is to reduce exposure by maintaining distance from people with the flu. And to reduce vulnerability, one could get vaccinated. So there are multiple levers for reducing risk again. We've seen that we can decompose risk in multiple concrete scenarios with this risk equation. Now let's try and do the same for analyzing the risks associated with machine learning systems. As it happens, we can associate terms of this risk equation with areas in machine learning safety. For example, the research area of alignment can relate to hazards because in alignment, what we're trying to do is reduce the probability and severity of inherent model hazards. For example, if an agent has an incorrect goal, that would make it a lot more hazardous. And we could remove that hazard by giving it a correct goal. So rather than have it choose wrong goals, which would be a hazard of the system, we can give it correct goals. And that will reduce the overall risk. Let's return to the risk equation. Vulnerability in the risk equation relates strongly to the research area of robustness. Robustness, I'll remind you, is about withstanding hazards and reducing vulnerability to them. So by decreasing susceptibility to hazards, we're reducing the system's vulnerability, and that reduces risk. So, as an example, here's an agent that came across a hazard and was vulnerable to that hazard that caused the system to break down. Another way that a system might be vulnerable to hazards is if it comes across the hazard, it might be redirected in an unfortunate direction. So this would be another potential risk that could arise from vulnerabilities. Having spoken about alignment and robustness, let's look at monitoring. Monitoring is associated with reducing hazard exposure. By identifying hazards, we can reduce our exposure to them and try to avoid them. So as an example, the robot in this situation can try and steer around potential hazards. Rather than trying to take the shortest path to the objective, it's taking a safer path. The fourth research area of systemic safety can influence multiple factors of the risk equation. That shouldn't be terribly surprising because systemic safety is quite broad and touches on a lot of different areas, and systemic factors permeate lots of considerations for machine learning systems. Let's look at an example of reducing some systemic hazard with a machine learning system. So by default, the models are trying to go to the objective, but with systemic safety, what we could do is we could actually just remove the hazards in the environment, and that would ultimately make it more safely pursue its objectives. Now let's look at an extension of the disaster risk equation for analyzing not just risks associated with machine learning systems, but getting a better sense of existential risks. So if the ability to cope in this equation goes to zero, that is, if we can never recover from a potentially catastrophic event, then the risk diverges and becomes unboundedly large. So, for instance, if an advanced AI system is misaligned with our values and is vastly more powerful than the other models combined, our ability to gain back control is low, so the ability to cope is near zero. That would constitute a scenario with unusually large risk. So this is one reason we want to avoid X risks, because they remove the ability to cope, and that tends to make them have extraordinarily high risk. Let's speak briefly about reducing risk in practice. Reducing risk in practice is not the same as estimating risk. While one might be tempted to spend many resources gaining a very precise estimate of risk, in situations already known to be high risk, this isn't necessarily the most cost-effective action. It might be the case that the situation is high inherent uncertainty, so that much precision isn't necessarily possible. It could also be the case that the precision increases are not that action relevant. That is, if we go from a 55% risk to a 54% risk, doesn't end up mattering that much for many real-world situations. What actually matters is identifying ways to reduce vulnerabilities, exposure, and hazards. And then one needs to prioritize among them, respond to them, and assess how one is doing. So rather than trying to get a very clear, concise model that estimates the risk, often one's mental energy should instead be spent on trying to just remove vulnerabilities and reduce exposure. So with reducing exposure, for instance, you might know that there are many factors that could lead to a bad situation. The sort of tinder is there. We don't know how the fire is basically going to be set off or express itself, but it is going to come if we don't reduce exposure to it. That's often the case in real-world situations. The hazards are there and they need to be addressed. We can get a more precise estimate, but that will often burn time. And by the time we end up getting all the information, it might be too late. So generally, in reducing risk in the real world, you often want to prioritize action somewhat earlier rather than really bolting down a precise risk estimate.